Welcome to G Fun Facts Online. Today we are stepping into what might be the most profound scientific frontier of our time. It is a place where biology and engineering collide, a concept known as the linguistic mirror. For decades, we have looked at the human brain as one mystery, and artificial intelligence as a completely separate field of engineering. But recently, the walls between these two worlds have crumbled. We have discovered that the artificial models we built just to write emails or summarize articles have spontaneously evolved a structure that mimics the human brain with terrifying precision. This is not just a coincidence, it suggests that we are uncovering a universal law of intelligence. Over the next 20 minutes, we are going to break down exactly how this happened, the specific brain regions involved, and the urgent ethical questions this raises for the future of humanity. Let us begin with the history of the divide. For most of the 20th century, neuroscience and AI were like distant cousins who never spoke to each other. Neuroscientists were working top-down. They had tools like fMRI scanners and EEG machines. They could look at a brain and say, hey, there is activity in the temporal lobe, or there is blood flow in Broca's area. But these tools were coarse. They could tell us where the activity was happening, but they could not tell us exactly what algorithms were running. It was like looking at a computer from the outside, measuring how hot it gets, but having no idea what software is installed. On the other side of the track, you had AI researchers. They were building their own black boxes. Early AI was symbolic. It relied on rules. You had to tell a computer that a cat has 4 legs and whiskers. This worked for chess, but it failed miserably for language, because language is messy and breaks the rules. Then came 2017. Researchers at Google published a paper titled "Attention is All You Need." This was the birth of the transformer architecture. Unlike previous models that read a sentence from left to right, often forgetting the beginning by the time they reached the end, transformers could look at the entire sentence at once. They used a mechanism called self-attention to weigh the relationship of every word to every other word simultaneously. This allowed them to build incredibly rich, context-aware representations of language. But here is the crucial detail. These models, like BERT in the early GPT systems, were not designed to mimic the brain. They were designed to beat translation benchmarks. Their creators were trying to improve Google Translate, not solve the mysteries of the human cortex. And yet, as these models grew, a strange phenomenon emerged. When neuroscientists compared the internal math of these machines to the internal firing patterns of the human brain, they found a match. This leads us to the discovery of linear mapping. This is one of the most elegant experiments in modern science. Imagine you are running a study. You place a human subject inside an fMRI scanner. You play them a podcast, perhaps a 30-minute story from the moth. As they listen, the scanner records the blood flow in thousands of tiny 3D pixels in their brain, called voxels. This gives you a massive timeline of biological activity. Then, you take that exact same story text and feed it into an AI model. You record the activity of the artificial neurons in the model's layers. Now you have 2 datasets, one biological, one artificial. Researchers found that they could use a simple mathematical translator to map one to the other. If the AI represented a sentence with a specific mathematical vector, researchers could accurately predict exactly what the pattern of blood flow would be in the human brain. The AI had inadvertently discovered the brain's own neural code. But the alignment goes deeper than just general correlation. It is hierarchical. This is where the work from labs at MIT and Meta AI becomes fascinating. Both the brain and the transformer process information in layers, moving from simple features to complex meaning. Let's look at the early layers first. In a transformer model, the first few layers are obsessed with surface-level details. They look at word position and basic grammar. They know that the word new is usually followed by York. In the human brain, this aligns perfectly with the auditory cortex. When you hear speech, your brain first processes the raw sound, the pitch, the volume, and the phonemes. The machine and the brain are doing the exact same thing at this stage. Structure, not meaning. As we move to the middle layers of the model, the attention heads start tracking long-range relationships. They worry about tense and agreement. In the brain, this activity shifts to the superior temporal gyrus. This is where sounds are assembled into words and phrases. Finally, we reach the deep layers. This is where the magic happens. The deepest layers of a transformer stop caring about the exact words used. They start representing the pure concepts. If you change a sentence from "the cat sat on the mat" to "the feline rested on the rug," the deep layers look nearly identical. In the human brain, this high-level processing happens in the language network, specifically Broca's area and the anterior temporal lobe. The studies confirm that the deepest layers of the AI are the best predictors of these high-level brain regions. The AI has learned to extract meaning in a way that is mathematically isomorphic to how you are understanding this sentence right now. This brings us to the semantic hub theory. Recent research suggests the brain has a centralized hub in the anterior temporal lobe that integrates everything. It combines what you see, what you hear and what you feel into a single concept. When you think of an apple, your brain fires a specific pattern for appleness, regardless of whether you are holding one or reading the word. Surprisingly, LLMs have evolved a similar structure. Even though they are trained on text, they develop a centralized, abstract representation space. This suggests that this hub-and-spoke architecture isn't just a biological quirk. It might be the fundamental geometry of intelligence. But why? Why would a silicon chip trained on Reddit threads resemble an organ evolved for hunting and gathering? The leading theory is called predictive coding. For a long time, we thought the brain was a passive receiver. We thought the eyes took a photo and the brain processed it. Predictive coding flips this around. It argues that the brain is a proactive prediction machine. Every millisecond, your brain is hallucinating what it expects to happen next. When you listen to someone talk, you are constantly predicting the next word. If I say, "I take my coffee with cream and," your brain has already fired the neurons for sugar before I even say it. This efficiency is crucial for survival. Processing sensory input is slow, but prediction is fast. By predicting the world, the brain only needs to process the error signal, the difference between what it expected and what actually happened. Now, look at how we train large language models. The objective function of GPT-4 is simply next token prediction. We force the model to guess the next word, and we punish it mathematically if it gets it wrong. We are forcing the AI to become a prediction machine, just like the brain. This shared objective, the goal to minimize surprise, is likely the cause of the structural alignment. It turns out, there are not infinitely many ways to be good at language. To predict well, you must understand syntax, you must track context, you must build a hierarchy of meaning. The brain did it with neurons to survive the savannah. The transformer did it with matrices to survive the loss function. But the destination is the same. There is, however, a critical difference. LLMs are typically unit predictive. They optimize for the very next token. The human brain is hierarchically predictive. The auditory cortex predicts the sound. The word form area predicts the word, and the prefrontal cortex predicts the narrative arc. Biological brains are still superior in this multi-scale thinking, though newer AI architectures are trying to close that gap. Now, we must turn to the implications of this. If AI models possess a map of the human brain's language processing, we are crossing a threshold that is as dangerous as it is exciting. We are unlocking the potential for neural decoding. In 2022 and 2023, researchers used this alignment to build a decoder. They took fMRI scans of people listening to stories and fed that data into a GPT-based model. The AI was able to reconstruct the story the person was hearing, often with startling accuracy. It wasn't just getting the gist, it was retrieving specific phrases and names. This is a double-edged sword. On one hand, it is a medical miracle. For patients with locked-in syndrome, people who are conscious but paralyzed and unable to speak, this offers a way to communicate. A non-invasive cap could translate their internal monologue into speech, restoring their connection to the world. On the other hand, it is a privacy nightmare. For all of human history, our thoughts were the one truly private space. Neural decoding threatens to make the mind as accessible as a web server. This has given rise to a new field called neurorights. Legal scholars are scrambling to propose fundamental human rights to protect us. These include the right to mental privacy, ensuring no one can scan your brainwaves without consent, the right to cognitive liberty, protecting you from forced decoding, the right to mental integrity, protecting you from malicious actors trying to insert thoughts or emotions via stimulation, and the right to psychological continuity, ensuring your personality isn't altered by technology. Chile has actually become the first nation to amend its constitution to include neurorights, explicitly protecting mental data. This is not science fiction anymore. It is a frantic attempt to build a levee before the floodwaters arrive. Finally, we must look at the future of the hardware itself. The transformer is a masterpiece, but it is physically inefficient. The human brain runs on about 20 watts of power, roughly the same as a dim light bulb. A large transformer training run can consume gigawatt hours, equivalent to the output of a power plant. The brain is also incredibly data efficient. A child learns language from a few million words, while GPT-4 requires trillions. This mismatch is driving the search for biologically plausible AI. One promising avenue is spiking neural networks, or SNNs. The brain doesn't use continuous numbers like a computer chip. It uses spikes. Neurons are silent most of the time, firing a discrete pulse only when necessary. SNNs mimic this event-driven behavior. They are incredibly energy efficient, because they only consume power when a spike happens. Researchers are now building spiking transformers that match the performance of traditional models, but use 100 times less energy. To run these, we are seeing the rise of neuromorphic computing. Companies like Intel and IBM are building chips that mix memory and processing together, just like biological neurons. When we run brain-aligned transformers on brain-like chips, we may finally close the loop. we will have machines that not only think like us, but work like us physically. New architectures are even moving away from rigid token generation to continuous thought machines, which model the fluid, evolving state of the world rather than just static symbols. In conclusion, the concept of the linguistic mirror reflects both ways. When we look into the AI, we see a reflection of our own neural architecture, a validation that our brains are prediction engines optimizing for meaning. But when we look into the brain with these new tools, we see the reflection of the machine, a biological computer that can be decoded, mapped, and potentially reprogrammed. We are realizing that intelligence is a physics-agnostic phenomenon. It does not care if it runs on the wet chemistry of carbon or the dry logic of silicon. The algorithms of understanding are universal. The challenge for the next decade is not just to build smarter machines, but to protect the sanctity of the biological minds that created them. We must ensure that as we build this mirror, we remain the masters of the reflection. Thank you for listening to G Fun Facts Online.